This is a supplementary video for section 8.2 on surface area. And I want to, the reason to give you this supplementary video is to give you some techniques to make life a little bit easier for yourself when you're asked to find a surface area. Okay? So let me go back and talk about the formulas that we had originally. So if I'm looking at rotating the graph of the function y equals f of x in the range between a and b, and I want to rotate about the x-axis, then the formula that we derived for that, or talked about for the surface area, is the integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. Okay. Now, what you see in this after the section on arc length is you recognize that this is the thing that we would integrate in order to find the arc length of the function. And there's a really nice connection with the arc length function, so let me write that over here on the side. So the arc length function, s of x, we defined to be the integral from a to x square root 1 plus f prime of t squared dt. And I said before that this was going to be useful. Here's the place where it's useful, because when I take the derivative of a function like this that's defined in terms of an integral from a to x, then the fundamental theorem of calculus part 1 tells us that the derivative of that function is simply gotten by evaluating the integrand at x. And so, if we call, instead of calling this s of x, we call this s, this tells me how to find ds, because ds, here's my formula for s prime, is the same thing as s prime times dx by definition of the differential. And so we have that ds is square root of 1 plus f prime of x squared dx. And so this quantity that we have over here in our integral, now including the dx, is simply ds, where s is the arc length function. And over here, f of x is the same thing as y. So the book does a very clever thing, which is to say s is the integral 2 pi y ds when you're rotating about the x-axis. Now the nice thing about this is that when you are, instead of looking at y equals f of x, but you look at x equals g of y, rotate about the x-axis again, and we'll use the range c less than or equal to y less than or equal to d here, that you have a similar formulation for the arc length function in terms of y. That should be a t inside the integral there. So I have an expression for ds here. And so if I look at this formula here with its y and its ds, I can find that the surface area in this case is the integral of 2 pi times y times the formula that I found over here for ds. Right. And notice I have to use y in both of these places because I'm integrating with respect to y over here. Okay, so if you have a situation where you're rotating about the x-axis, you get to resort to using this formula. And what you have to decide is you have to decide whether you're going to write y, as we've done over here, or whether you're going to write y as f of x, as we've done up here. And then you also have to deal with the limits of integration. In this case, we would go from c to d because we're integrating with respect to y. So let me show you on the next couple of pages how this would work in... I need to give you the formulas for rotating about the y-axis. So let me do those because I want to touch on an example that we did in the group work when we worked on the section 8.2. So if you rotate about the y-axis instead of about the x-axis, then the formula you get without limits of integration is 2 pi times x times ds. And now depending on whether you have a y equals f of x situation or a x equals g of y situation, that tells you what to put in for x down here, what to put for ds down here, and what to put in for the limits of integration. And so the two formulas that we get for this is we get that s equals the integral from a to b, if I'm going to integrate with respect to x, of 2 pi x times the version of ds that uses x's. Or if you're doing things in terms of y, we'd integrate from c to d, 2 pi g of y square root of 1 plus g prime of y squared dy. And those are pretty convenient formulas, and I'll show you why when we go through this example. So the example is to look at the function y equals 1 minus x squared in the range 0 less than or equal to x less than or equal to 1, and we're supposed to rotate about the y-axis. And so our formula in this case is that the surface area is the integral of 2 pi times x times ds. And we're going to do this in two ways. So the way that I had suggested in class to some folks that they should do it is, so method 1, and this is the hard way, is to use the y equals f of x formulation. No, that's not what I suggested. I suggested to do the x equals g of y formulation. And that's because that original formula that we had allowed us to rotate about the y-axis only when we had the x equals g of y formulation. And so for that I needed to solve for x in terms of y. I original function. So we'd find that x squared equals 1 minus y, so x equals the square root of 1 minus y, because x is greater than or equal to 0, so I take the positive square root. And so now I need to change my x values into y values, and that would translate to 0 less than or equal to y less than or equal to 1. Right, and so my surface area formula in this case would be the integral from 0 to 1, these are y values that I'm using, of 2 pi times x, which is my square root of 1 minus y function, times the square root of 1 plus, now I have to do g prime of y squared dy, where this is my g of y. And that ends up being a big mess of quotient stuff. What you end up with, once you do the algebra, is the integral from 0 to 1 of 2 pi, square root of 1 minus y, times the square root of 5 minus 4y over 2 times the square root of 1 minus y dy. And I'm skipping the part that makes this method particularly hard. It's the algebra that's a pain in this particular example. Because at this stage what you can do is you can cancel nicely, and you get, when you, let's cancel those 2's as well, we end up pulling the pi out, integral 0 to 1, square root of 5 minus 4y dy, which we can evaluate using a u substitution. And we get, so let's see here, minus 4y has to be compensated, so minus pi over 4, integral, with the limits of integration changing to, down here, 5, and then 1 of the square root of u du. So that's u to the 1/2, and you can integrate that using basic techniques. Method 2 gives us slightly easier algebra, and then an integral that's not any harder. So method 2 is the y equals f of x formulation. And so my surface area is, I'm going to integrate with respect to x, so I integrate from 0 to 1 because those are my x values, and I do 2 pi times x times the square root of 1 plus f prime of x squared dx. And now you notice that maybe the whole point of this is that this is my f of x, and taking the derivative of that and squaring it and adding 1 is really easy. Okay, so what we end up with over here is the integral from 0 to 1, 2 pi x, square root of 1 plus 4x squared dx, which you can integrate using a u substitution over here of u equals 1 plus 4x squared du equals 8x dx. And so we end up with, now to compensate for the 8x, we have a pi over 4 integral. And now what happens with the limits of integration? Here we get 1, and here we get 5 of square root of u du. And notice that these two integrals here are the same. And the point is that, again, taking the derivative of this function is very easy. Taking the derivative of this function, it's not terribly hard, but it's not as easy. And then, when you plug the derivative into this expression, you have to do a lot more algebra than when you plug into this expression. Okay. So the method that you use totally depends on your preference. Either one will give you the correct answer, but one of them has much easier algebra, and so you're less likely to make mistakes with that second method. Right? So that's the end of the second lecture on surface area. Make sure and practice some problems with this.